A highly energetic particle found in Antarctica appears to have come from a star being ripped apart by a black hole. Astronomers on the hunt for a big black hole have found a nest of small ones. And a dedicated bushfire satellite is aiming for launch next year. The technology on board could detect fires within minutes of ignition. It's Tuesday, the 2nd of March, 2021.
On Apple Podcasts, Spotify, Google Podcasts, and YouTube. With the latest science and space news, this is Talkin Science with Dr. Brad Tucker and Matt Miller.
Welcome to Talkin Science. It's another instalment of the Science and Space News. Matt Miller with you. Dr. Brad Tucker is here. Brad, happy Tuesday.
How's it going?
Really good, my friend. Well, it's been a week where Sabre Astronautics, building Aussie Mission Control, have signed up with the Weather Bureau for real-time space weather. An Aussie collab fired up an experimental engine, and the Uni of Southern Queensland has teamed up with NASA for research into Martian crop growth. Everywhere we look, the tagline of this show is proving itself: science never sleeps.
Yeah, there's a lot going on. It's a busy world in space and on Earth.
Well, before we get into the show, a quick reminder of the socials. We can find you on Twitter at btucker22. I'm on Twitter at Miramat86. And of course, Trekzone exclusively on Twitter. And the YouTube channel where we're uploading video episodes of our podcasts. And those podcasts are everywhere you are. Just search for Trekzone. Dive in, subscribe, and ring the bell and do all that good stuff so you never miss a moment of Trekzone podcasting. Brad, let's dive into the show. First up, Australia has signed another memorandum of understanding, this time with the motherland, the UK, to allow space industry collaborations.
Yeah, they're calling this the bridge. This is really an expanded agreement that they've had before. And really what the focus on is on getting businesses and industries in both countries to work and bid and support projects in both countries. So really the name of the game here is often when you develop something, especially as a business or an industry or a product, it's sometimes hard to get picked up by a different country. Here, they're trying to essentially solve that issue so they act seamlessly together, which means that contracts and projects can be more widely sought and bid after and supported in both countries. And so there's a great reciprocal benefit in both of these.
Well, new research on the 1987 supernova in the Large Magellanic Cloud has turned up some evidence that there may be a pulsar in its heart.
Yeah, so 1987A, the closest supernova that we've had to Earth in almost 400 years, over 400 years technically, a really well-studied supernova. And we know that it was somewhat of a massive star, a blue supergiant, and been trying to find the remnant of that explosion. We've seen the explosion or the gas that's gone out into space, trying to pinpoint the leftover potential neutron star, which is often produced in these explosions and sometimes produces a pulsar, which appears to be the case that it may have finally been pinpointed. So really starting to see the evolution of a star, because this object, because it was so close to the Earth, there was imaging of this galaxy, our neighbor galaxy, the Large Magellanic Cloud. So we saw the star pre-explosion, saw the explosion, and now we're seeing the aftermath of what happened. So putting that whole picture together.
Well, moving into the stories of the week now, a ghost particle that crash-landed in Antarctica has been traced back to a star shredded by a black hole. This is a violent story.
Look, so these ghost particles, as I call them, neutrinos, there's neutrinos flying through you right now. They're these high-energy particles, don't have a lot of mass, travel quite fast, and we know they're produced by all sorts of things. 1987A, the nearby supernova, produced exactly 24 of them that we picked up here on Earth, able to count all 24. The sun produces lots of neutrinos as well. And in particular, we can measure how much energy they have, how powerful they are, which is somewhat relative to how far they've traveled or what source created them.
As you say, trillions of these neutrinos passing through us every second. This particular one from October 2019 landed in Antarctica right next to a very sensitive detector, so very convenient.
Yeah, and this is kind of one of the reasons why it was these sort of things were built there, because as these neutrinos travel through things, the crust, the Earth, we all slow these neutrinos down. So the more it goes through layers, the more energy it had to make it through those layers. Kind of think of a car crash. The faster the cars go, the more they collide. And by looking at IceCube, this array of detectors in the ice of Antarctica, which has been trying to find a number of these sorts of particles, able to find it. And then the hunt really began of what was the source. Was there something they can see that happened around the same time and in the rough, vague location, because they can kind of pinpoint roughly where in the sky it happened? In this case, using data from California in a survey trying to find them, the Palomar Transient Factory, able to pick up that it was indeed one of these black holes ripping apart a star.
Now, it's the violent end of the star, but a brilliant start for astronomers. What more can we learn from the research into this?
Yeah, look, there's been a lot of work into trying to find these tidal disruption events the moment these stars are destroyed by the black holes. And in a lot of cases, not too dissimilar from this nearby supernova that we had in 1987A, the neutrino escapes first. Not that it travels faster than the speed of light, but they leave the center. They get out of Dodge at their earliest moment. And then it takes time. It literally takes minutes to hours for the rest of the star to explode or be ripped apart and travel into space. So the first moment kind of danger is happening on this star. The neutrinos inside, deep inside, much like the neutrinos from the sun that hit us, leave. So we see those first. And then you can use that knowledge to say, all right, well, when was the event that was occurred in it? Now, these tell us a lot about, again, the power, the energy needed to create them, to destroy them, to accelerate them through space. But also at the same time, by finding neutrinos, we don't have that many we've detected, especially from very far away, tells us about the nature of this quite mysterious particle. There's a lot of work going into understanding neutrinos, from exactly how many there are or different types to what exactly creates them. So the more we can find the particles and pinpoint the source, it gives us a lot of bit of picture of connecting these two fields, what we call particle physics, the very small things that make up the universe, and astrophysics and space.
And this could help answer a question that's been hanging around astrophysics since the 60s, just exactly where these particles are coming from, and building our understanding of all these things that are out there in space that are maybe out to kill us, maybe certainly out to pass through us.
Yeah, they're not unique, and the problem is, just trying to find the rough needle in the haystack, where it even came from in space and time, and you don't even know what you're looking for. So this is the sort of new thing that we can do when we're looking at different types of exploring the universe. Gravitational waves being another great example. The goal now is to get some sort of event that explodes where we can see the explosion through optical telescopes and potentially radio and others, see or measure the gravitational waves that hit the Earth, and measure the neutrinos. That's kind of now the goal, is to combine all those three, because they measure different types of physics and science. And by combining them, you get a bigger picture together of what is going on.
Well, next up in our stories of the week, Brad, scientists were looking for a big black hole. They've seemingly found a nest of small ones. Now, this gives me a bit of some vibes from sci-fi shows and movies where our heroes go into a cave full of bugs and it's a nest of stuff going on. But it's not kind of like that. There's black holes, and there's a whole heap of them in a very small relative area.
That's right. So, they were looking at an area, what we call an old globular cluster. And what they were trying to see is, was there some sort of more larger black hole, not quite a supermassive black hole, but, towards it, what we call sometimes intermediate mass black holes, arranged between the star-like black holes, the smaller masses, and the big ones. And we know at the center of every large galaxy, there's roughly, we think, a supermassive one. And by looking at this cluster, this what we think is a remnant galaxy potentially, by seeing a whole bunch of these small black holes, was quite interesting, because there is this theory that over time, these small black holes merge together to form the bigger ones. So this may be part of this action happening in somewhat real time.
And part of the research into finding this nest of smaller black holes, was studying thousands of stars and working out how they were moving under the influence of some invisible force pushing their gravity along. And I guess they were looking. That's why they were looking for this one big black hole. But seeing how all these stars were moving erratically, came up with the nest, and this is where we're finding all these smaller black holes. And as you're saying, we might have a better understanding now of how these black holes grow up, as it were.
Yeah, because this cluster is an old one. It's 13 billion years old. It's one of the first ones formed with very old stars. And so we know old stars eventually form and die. And based on the previous motions and data, they said, well, maybe there was about a black hole about 600 times the mass of our sun. So getting into that intermediate mass range. But as you said, and when they realized the motions of it, thanks to this really cool telescope called Gaia, which is a space telescope measuring the precise orbits and motions of stars, able to realize they weren't moving around just one thing, that, as he said, it was a bit chaotic, that there was a whole bunch of activity going on. And you just never really seen this before, let alone there's a big work into finding black holes into clusters, because there's a lot of debate about these globular clusters, whether they're always old galaxies, or the remnants of galaxies, or they're their own things, or somewhere in between.
And this discovery could give us a source of gravitational waves as well.
Yeah, look, these things eventually over time will potentially collide and crash into each other and form, again, these bigger black holes. Now, in this one, we probably won't necessarily detect gravitational waves. It is possible. But here, the big question is, in seeing these sorts of things, by seeing a cluster that has lots of black holes, that idea that these mergers can happen shows that there are potentially other ones like this. It's probably unlikely that this is the only one out there in the universe.
And we've talked about merging black holes in the past here on Talkin Science, the way these are forming and the life cycle of black holes, as it were. So this could be a great one to watch to see what these black holes are going to be doing.
Yeah, look, is there signs that you'll start to see ripples or changing of the environment, any sort of collisions, but also further studies to try and pinpoint better the positions, the motions, and the masses of these black holes, in addition to kind of the rest of the dead stars that they see here, because again, they can measure that there's probably these white dwarfs and neutron stars. So the old suns and the old big stars that explode. So it's really a great example into what happens at the ends of lives of stars in an area that is contained. What happens essentially when maybe a small galaxy kind of starts to die.
And lastly this week, Brad, Queensland-based Fireball International is in talks with the Australian government to bring their bushfire detection technology here in satellite form to really help us get a hold of some of the larger bushfires that we have in this country.
So Fireball is a group I've touched base and worked with quite a lot, and it's using AI and machine learning. They've been doing this firstly on just towers, starting it out actually through some astronomers in California. Carl Pennypacker was a big one here, who also does Supernova, and like me, and trying to use it to find the moment a fire ignites, just as we want to find the moment a star ignites or explodes, the moment a fire ignites. And when you can see that, then if you can capture it early, pinpoint the location early, you can get onto it and then hopefully get it under control a lot faster.
It's interesting technology and really proving the point that science is helping us understand Earth, science around the galaxy and the universe. Now, there was a little bit of a trending topic on Twitter when Perseverance landed a couple of weeks ago about, yeah, that's great, but we should be focusing on Earth. And this is just a clear demonstration that that looking out and looking beyond is worthwhile because it helps us back here on Earth, and it's already proving itself in California.
Yeah, look, using some of the techniques that we use to find things in the nighttime sky, and the computer techniques and the imaging techniques and the colors of light, and then doing it in a very applicable way. And when we talk about what space is for, if you want to look at a larger area, you have to go higher. That's just point blank the name of the game. And that's the whole point of putting these things on a satellite. The towers are great in seeing in a contained area, but if you want to look at a larger area and see more of it, you have to go higher into satellites. And that's what this whole point is about. It's not just exploration, but there's a whole huge range of other purposes. And this is a great example, one that is very relevant, that, if you had this sort of technology in the bushfires that we had back in 2019 into 2020, instead of waiting hours in some cases, or maybe even longer to know where or get stuff to a fire, if you're knowing it within some of their cases 60 seconds, that it dramatically changes the size and the nature of the fire. And it's proven to be doing and working in these things again in some of the rollouts that they've done in California.
Well, last summer was dubbed as Black Summer, with so much of Australia's east coast and parts of Western Australia ravaged by bushfires that were out of control. Authorities unable to save many homes and livelihoods, and some lives were lost. Taking this observatory into orbit, not relying on ground-based detection, I guess is key, as you were talking about, to get a bigger picture of the overall lay of the land. Somewhere like Australia is a perfect proving ground for this sort of technology, being so open and so sparsely populated.
And look, there have been other satellites that have been used in fires, and they've been doing especially important for fuel loads and predicting where the fire is going to go and those sorts of things. And this is really trying to be building a dedicated mission for Australia. So instead of reliant on a satellite going at lots of different areas and maybe getting coverage only every couple of hours or every couple of days, they're doing this, pretty much every orbit over a large area of Australia. And so it's another tool for firefighters and emergency services to use to better understand what's happening. And this technology directly transfers into other areas. You can imagine this sort of thing rolls out in what we see in just monitoring water, or as we were talking about with bushfire loads, vegetation, dryness, helping for farmers. So there's a huge expandable range when we go into space and do these things. So it's not just sending rovers to Mars, which is cool as it is. There's a lot of just practical benefits that a lot of people are working on and trying to dual purpose something that they've used for a completely different other reason into something very practical. In fact, I know other astronomers in the UK, for instance, trying to use the AI detection algorithms to now turn it to the human body to find early cancer and tumor cells. Oh, wow. Again, it's the same concept. If you want to find the needle in the haystack black hole, you can find the needle in the haystack tumor as well. And there's a lot of that thinking. And I think that's the great thing holistically about science. It's not necessarily just about what you do at the end. It's the process and applying it to different problems.
Well, launch specifics are still being worked out, but the Space Machines company has signed a deal to take the payload aboard Optimus 1, which will be powered in flight by Gilmour Space rockets. It's going to be an Aussie mission, which is very, very cool.
And then I think this is kind of the amazing thing when we start to see the evolution, especially in space in countries like Australia and the private sector. You're able to do these things now more and able to do them with a focus and ultimately for relatively dirt cheap in the grand scheme of things that you may not normally be able to do.
Brad, another week of Talkin' Science, another big week, in fact. As always, it's great to pick apart those stories of the week with you. We're going to do it again next week. Thanks for being here.
Thanks.